Hello everyone, this is Mr. Kazi coming from my virtual studios in beautiful Humboldt, Texas. And what a beautiful day we have out here today, and I'm bringing you another lesson in chemistry. This one is on IMFs and polarity. That's intermolecular forces and polarity. So, get your periodic table and let's get started. In this lesson, you will learn about polar bonds, nonpolar bonds, polar molecules, and IMFs, or intermolecular forces. As usual, you'll need a periodic table, and you must know valence electrons, possible charges, electronegativity, chemical bonding, and molecular shapes. And if you haven't got any of these down, then be sure to go to Mr. Kazi's YouTube channel and watch some of the other lessons on these very topics. Polar means having opposite ends like a battery or a magnet. Or you might look at the little energy cells that you use for running your iPods and things of that nature. Whatever might use your cells. That's going to have two ends, a negative end and a positive end. And that is polar. Okay? So we're looking for something with opposite ends or opposite charges. A polar bond is a covalent bond in which the electron pair is not shared equally. And because it's not shared equally, it's creating a partial charge. Now, it's not a full charge or a big charge like an ionic charge, but it's a charge where the oxygen in an oxygen-hydrogen bond might be getting the electrons a little bit more than the hydrogen. This is called a polar bond, because what you do is you create a little bit of a charge, a negative charge on the oxygen, and a little bit of a positive charge on the hydrogen. An example of this might be the carbon-hydrogen bond, and carbon has the higher electronegativity, so carbon gets the bigger share of the electrons, creating a partial charge, and that would be negative. Remember, electrons are negative, and then making hydrogen partially positive. So this is a polar bond. A nonpolar bond is a covalent bond in which the electron pair is shared equally. Nobody has it more than the other. Their electronegativities are either the same or very close. And an example of that would be a carbon-to-carbon bond, or an oxygen-to-oxygen, or a nitrogen-to-nitrogen. Both have the same electronegativity, so they share the electrons equally. Nonpolar. Now let's talk about polar and nonpolar molecules. Once you get the idea of the polar bonds down, the polar bonds help us understand polar molecules. And remember, molecule refers to covalent bonds or covalent compounds. Polar or nonpolar? Well, first of all, draw the molecule. Then include electron pairs. Determine the partial charges according to electronegativity. And look for balanced areas. Look for unbalanced areas. Now, if it's balanced or symmetrical, it's going to be nonpolar. But if it is going to be unbalanced in areas where one side is negative or another part is positive, now we're looking at polar. A polar molecule is a molecule with a positive and negative region. It's unbalanced. And it'll be polar bonds and electron pairs that determine this. Example, let's look at ammonia here. Notice you have nitrogen bonding with 3 hydrogens. It has that electron pair. Well, because of that electron pair now, we're going to have somewhat of a negative charge forming there. Nitrogen has the higher electronegativity and a lone pair of electrons. That's going to create a negative and positive region as hydrogen gives the electrons more to nitrogen. Now, it doesn't give them up, but it's just not sharing equally. And that's a polar molecule. Example of a nonpolar molecule is going to be a molecule with symmetrically balanced charges, and it's going to balance out. Let's look at an example here. We have carbon, which has a little bit higher electronegativity than hydrogen. And, you know, if you've been studying your periodic table and the periodic trends, you should be able to look at that and realize carbon is probably a little bit more electronegative than hydrogen. Not a lot, but a little bit more. And you can always look up in a reference book to check if you're not sure. But carbon has the higher electronegativity. thereby creating on the outside all these positive charges. Now, the charge over here in the middle, that's not on the outside. It's not creating a polar end. This here is going to be a nonpolar molecule. And most of your symmetrical molecules are going to be nonpolar. Let's do a little practice. Are the following nonpolar or polar? Water, polar. Let's go see why. Oxygen is more electronegative and has 2 pairs of unbonded electrons. That would create a negative end. Hydrogen shares with oxygen and becomes partially positive. And so what do we get? We get a positive or partially positive region, and so a polar molecule. Let's practice another one. Arsenic trichloride, nonpolar. Now you see there's arsenic, and it's bonded 3 times with its chlorine and has a lone pair right up there. Chlorine is more electronegative, creating a partially negative charge. And arsenic has lone pairs of electrons, creating a partial negative charge. The charges are symmetrically balanced, and this creates a nonpolar molecule. All right, IMFs, intermolecular forces. What holds all these molecules together? Intermolecular forces are physical attractions between molecules. Now, this is not a chemical bond or a chemical attraction. This is a physical attraction between the molecules caused by dipoles, by momentary positive and negative charges coming about and creating a type of attraction. So it's an attraction. IMFs are not chemical bonds, and there are 3 types of IMFs: dispersion forces, dipole-dipole forces, and hydrogen bonds. Let's look at dispersion forces. Attraction between temporary dipoles caused by the movement of electrons in the atoms of a molecule. What happens here, in some molecules, the electronegativity may not be very strong, but there's still electrons there, and those electrons are still moving about, and sometimes they may be moved towards one side of a molecule, and that will create, or side of an atom, and that will create a momentary positive charge or negative charge, thereby causing a positive or negative charge in another molecule or atom. And because of that, we have these momentary, quick, temporary dipoles that have an attraction to each other. They're present in all molecules, very weak, and stronger in larger molecules. Dipole-dipole forces are attractions between 2 polar molecules, or dipoles. And this is an intermediate strength, a little bit stronger than the dispersion forces, but nowhere near as strong as the hydrogen bond. And they are in all polar molecules. So you have dispersion forces which appear in all molecular molecules and compounds, but the dipole-dipole forces are only going to be in polar molecules. The hydrogen bonds. Now they're the strongest of the 3 IMFs, and it's attraction between polar molecules that contain hydrogen atoms bonded fluorine, oxygen, nitrogen, or chlorine. And I believe this is probably created by the very strong electronegativity of fluorine, oxygen, nitrogen, chlorine, and their pull on hydrogen, creating very strong dipoles. And very strong dipoles creating very strong attractions between each other. It's kind of like really strong magnets, really pulling in on each other. And the hydrogen bonds are the strongest of these IMFs, and it's hydrogen bonds that give water so many of its neat characteristics, like the ability to pour water up to the edge of a glass and even a bit over the edge before it spills over. So very cool. All right, let's do which IMFs are present in methane, CH4. Which IMFs are present here? Well, it's nonpolar, so dispersion forces only. Can't have dipole-dipole or hydrogen bonds unless it's polar. Let's look at another one. Water, H2O. Water's polar. It has dispersion forces, dipole-dipole forces, and hydrogen bonds, and makes it very strong. As far as IMFs go, they're nowhere near ionic or covalent bonding. You got any questions? Send an email to Mr. Causey at mrcausey.com. Be sure to check out my website, mrcausey.com or mrcausey.info. Also, don't forget to subscribe to my YouTube channel. Check out some of the other videos. All right, happy ions.